Hello all, welcome to the Digital System Design Lab. Today we are going to understand the experiment number 8. Experiment number 8 is realize the following shift registers using IC7495. So the shift registers we are going to be analyze are SISO, that is serial in, serial out, serial in, parallel out, parallel in, serial out, and parallel in, parallel out, and ring and Johnson counter. So first let's understand the words register, shift register, and then 7495. Okay, then we will going to implement these following shift registers using the IC 7495. So first of all, register is a collection of a flip-flop in cascade. Okay, cascading of flip-flops, that is what is a register. Example, if you consider a D flip-flop, this is, and this cascade with another D flip-flop, and this is called as actually a register. So it is a 2-bit register, so that means it can store a 2-bit data. Registers are used to store a data in digital systems. 2 registers can store a 2-bit value, so that means this can store a value 00 to 11. So similarly 3 registers are cascaded together, they can store a 3 values, that is from 000 to 1111. Okay. Similarly 4 registers can have store a 4-bit data, okay, that is from 000 to 111. Okay. So that is called as actually a register. Okay. So data stored in the registers are called as states or a content of an register. Whatever the data is stored in the register, that can be moved from the left to right or a right to left. That means if you can able to shift those values, then that registers is called as actually shift register. Shift register, registers that are capable of moving the information upon the occurrence of an clock signal. So as the clock signal is given, so whatever the data stored in the registers can able to shift in either side, left or a right. Okay, then that is called as a shift registers. So as the data can be moved from the one direction to another direction. Okay, so there are 2 types of in the shift registers. Okay, if we classify the data, we transfer from the one direction to another direction. There are 2 types. One is called as an unidirectional, another called as an bidirectional. So unidirectional shift registers means they can shift the data from the only to the one side to other side. That means left to right. So left shift registers will always going to shift the data from left to right. So that is what a unidirectional shift registers. So another is what the bidirectional shift register. So in a bidirectional shift register, the data can be shift from the right to left or a left to right. Okay, that is called as a bidirectional shift registers. So this is the classifications of the shift register based on the transformation of the data. Again, shift registers can also be classified based on the how we are entering the data into the shift register. There are 2 ways to enter the data. So one is called as an parallel, another is called as a serial. So in parallel, all the symbols are 0 or 1 will be given parallelly to the all the flip-flops. Okay, so that is what is called as an actually parallel input. Okay. Similarly, in a serial, so that involves the symbols by symbol available of an information in a time sequence. Okay. So where the data will be given in a serial. So after 1 by 1 symbol will be given. Okay. So that is what then 2 ways we can give. By considering the 2 ways, we have 4 types of shift registers. Okay. If we classified based on the how we are giving the data. Okay. So 4 possible ways registers can transfer the information. So one is what? Serial in, serial out. So we are giving the data in a serial and we are taking the data from shift register in a serial. So that is what the serial in, serial out. So another is serial in, parallel out. We are giving the data to the shift register in a serial, but we are taking the data output parallelly. That is what the serial in, parallel out. Okay. And another is what? Parallel in, parallel out. Another parallel in, serial out. Okay. So these are the 4 ways we are going to have. Okay. And these 4 ways will going to be realized in the IC 7495. Okay. So let's understand what is in 7495. So before understanding the pin diagrams of an IC 7495, let's understand how the shifting action will going to take place. Okay. How the serial in, parallel out, how that means, let's see it in a diagrammatic way. So this is an 4-bit serial in, serial out shift register. So here the 4 flip-flops are connected. Okay. So we are giving the data in a serial, okay, and taking the data in a serial. Okay. So as the clock is given, first data will going to be stored in this flip-flop. Okay. Next clock pulse, so second data will be stored and the previous data will be moved to the next flip flop. Okay. Like this the data will going to be shift. So that is what is serial in, serial out. Okay. Similarly, this is an serial in, parallel out. So we are giving the data serially and we are taking the data parallelly. Okay. So that means all the outputs of the flip flops are connected to the outputs. So as the serial data given, so parallelly we are going to take the data. Okay. So this is what the serial in, parallel out. So parallel in, serial out. All the inputs of the flip flops will be given parallelly and the data will be taken in a serial. Okay. So this is what the way here we are going to use some extra additional circuits we are going to use to make then parallel input connections. Okay. So similarly, we have an universal shift register. Universal shift register it can perform an left shift, okay, and even we can perform an right shift. And even we can give the data in a serial in or a parallel in, and even we can take a data in a serial out or a parallel. All the combinations are involved in a one circuit that is called as an universal shift register. And this is a circuit of an universal shift registers. So here we can give the serial data in a left shift or we can perform an right shift also, okay, and even we can give the data in a parallel input, even we can take the data in a parallel output, or even we can give the data in a serial. Okay, all the functions can be done. Okay, here we have used the 4:1 mux. Okay, so these select pins of the mux will be act as a mode pin, where we can change the mode of the operation, serial operation or a parallel operation. Okay, the shift register should be work as in serial mode or in a parallel mode that can be controlled by using the mode pins. Okay, that is what here. Okay, so this is the circuit which consisting in the IC7495. So what is a 7495? So 7495 is an 4-bit shift register which can perform an serial in, serial out, parallel in, parallel out, parallel in, serial out, parallel in, parallel out. Okay, all the operations can be performed in one IC. So that is what the IC7495. Okay, so let's understand the pin diagram of the IC7495. Let's understand about the IC7495. So 7495 is an 4-bit shift register which can perform then serial in, serial out, serial in, parallel out, parallel in, serial out, and the parallel in, parallel out operation. Okay, so this is the pin diagram. So which is having an serial data input line, okay, and the to give the data values in a parallelly, okay, we have the 4 inputs, and these 4 inputs corresponding to the 4 inputs of the flip flops. Okay, if you are having a D flip flops, okay, whatever the input needed to give in for the 4 flip flops, so these are the datas, where A corresponds to the MSB flip flop, where the D corresponds to the LSB flip flop. Okay. And we have the mode pin, so that is what the M. Okay, so the has already said mode pin will be used to perform an parallel operation or a serial operations. Okay, so if the mode pin is 1, so it will go to perform in an parallel operations. Okay, if the mode pin is 0, so for the serial operations, because as already said 7495 can perform an serial operation also and the parallel operation also. So that's why we are having this mode pin. Okay, and the pin number 7 is ground. And we have the 4 outputs corresponding to the 4 flip flops, that is a QA, QB, QC, QD, and we have a 2 clocks corresponding to the serial operation and the parallel operation. Okay, clock S corresponds to the serial shift and the clock P corresponds to the parallel operation. Okay, and we have the VCC. So this is the pin diagram of an IC7495. Okay, so first we will move to the to realize the serial in, serial out by using the IC7495. Okay, so this is the IC7495. Okay, so here we realized that the 7495 to implement the serial in, serial out. Okay, so here for the serial in, serial out we need only the serial data input, okay, and the last output. Okay, and then we need the operation mode pin should be operating in a 0. Okay, so this is what mode will be equals to 0, okay, and the VCC and the ground will be given, and the clock bus will be given to the pin number 9, okay, that's what the clock bus serial, so that clock bus will be given to the serial clock, okay, and the input whatever the data we need to be serially we need to give, that data will be given to the serial data line. Okay, so and we are taking the output from the QD. because in a serial in, serial out, okay. So where the data will be given into the first flip flop and the data will be taken out in the last flip flop. So that's why, so we're going to consider the data in the last flip flop, that is in the QD. Okay, so whatever the data will be there in the QB, QA and QB, QC, so that will be shifted and that will come to the QD, and this data will be considered as an serial out. Okay. To analyze this serial in, serial out operation, so this is the two table you have. Okay. See, so when the time is 0, okay, when you give the logic 1 is given to the serial data line, and if you apply the clock pulse, okay, so that means first data will be stored into the first flip flop. Okay, so that means assuming we have a 4 flip flops here, Q, D, Q, okay, and this corresponds to the A, B, C, D, that means QA, QB, QC and the QD. Okay, here we are giving the serial input and we are taking the here serial output. Okay, so and as usual clock will be there. Okay, if you give a logic 1 here and apply the clock pulse, then this data will be stored in the first flip flop. So that will go to available in the first flip flop. Okay, and again whatever the next data if you will given and apply the clock pulse, and the second data will be stored in this flip flop, and whatever the data will be there in the first flip flop, that will be shifted to the second flip flop. Okay, so that means the 0 will be stored here and the 1 that will be transferred to the next flip flop. Okay, this is what an serial operation. So this is what will going to take place. So this is what we summarized here actually. When the time is t naught, if the inputs are 1 0 1 1, so first I will going to give the 1, okay, and then apply the clock pulse, okay, then this data will be available in the QA. Okay, when it comes to the next clock pulse, okay, if you give the input is 0, then this 0 is available in the QA, and whatever the data will be there in the previous, that will be shifted to the next flip flop. Okay, that is available in the second flip flop QB. Similarly in the next clock pulse, so if you apply the input is 1, so this is available in the QA, okay, the previous QA will be shifted to the QB and the previous QB will be shifted to the QC. Okay, similarly when you apply the next clock pulse, that is the fourth clock pulse, okay, then if 1 is given, then that will be available in the QA, and this will be shifted to here, and this will be shifted to here, and this will be shifted to here. So that means we got the first value of our serial input. So whatever the first digit we have given here, that is available in the output after the 4 clock pulse. Okay, if you give the 4 clock pulse, we are going to get all the outputs. That is what the serial in, serial out operation. Okay, so when you apply the next clock pulse, we are going to get the next bit which is having the serial input at second one. Okay, this is going to available here. On that time, whatever the data will be given, that will go to available in the QA. Okay, we can give a 0 or 1. So that's why here indicated with the X, don't care what it may be the value. Okay, we need to concentrate on the output. Okay, so there is 0 will be shifted here. So in the next clock pulse, this will be shifted. So we are going to get this serial out. So on the next clock pulse, we are going to get the last bit. So this is how we are going to get our input 1 0 1 1 at the output QD 1 0 1 1. Okay, so this is what an serial in, serial out operation. Okay, so next let's analyze the serial in, parallel out. So next we'll move to the serial in, parallel out. Okay, we are giving the data in a serial and we are taking the data from the shift register in a parallel. Okay, so this is how we're going to do. So we are giving the data in a serial, but in the parallel only we're going to take the data. Okay, so as the data will become, so that will going to appear in the output. As the data will available into this flip flop, we'll get the data. Similarly, as the data will shifted to here, we're going to get the data. Okay. Since we are doing the operation in a serial, so we need to keep the mode pin to the 0. Okay. The clock bus will be given to the serial clock. Okay, and the input will be given to the in the serial data in. Okay, but here we have to use all the outputs because we are taking the output in a parallel. Okay, when you are taking only in a serial, we have used only the QD. because whatever the intermediate outputs will be there, QA, QB, QC, there is no need to bother about that time, because we are doing the serial in, serial out. So in a serial in, serial out, we are taking the output at the last. So that's why we used only the QD. So but here we need to use all the outputs. Okay, so that's why even we need to connect the QA, QB, QC, QD to the our output logic circuits in a trainer kit. Okay, but when in the serial in, serial out, we need to connect only to the QD. Okay, here we need to connect to the all the outputs should be connected. Okay, now we need to make the connections in this way for the IC7495. Okay, and then apply the mono clock bus. When you apply the mono clock bus the first time, and when you giving the data is in the logic 1 in the serial data, and that will going to appear in the QA. Okay, and next when you apply to the data into the next clock pulse, okay, so that is our data will going to available as a 0, and then this 0 is available in the QA, and the QB will going to have the next shift value. Okay, so that means initially 1, so apply the clock pulse and we will going to get a 1 here. Okay, so next if we give the data is 0, apply the clock pulse, this 0 will available here and the 1 will be shifted to here. Okay, so again if you give the clock input is 1 and apply the clock pulse, okay, then this data will be going to be available here, and this data shifted here, and this data will be shifted to next flip flop. Okay, so this one by using the 4 clock pulse only we can get the output. Okay, but in a serial in, serial out, we used to take the 7 clock pulses, right? So at the 7 clock pulse we will going to get the our serial in data, serial out. Okay, but here by applying the 4 clock pulse only we will going to get the outputs. Okay, that is what 1 0 1 1 1 0 1 1 we will going to get. Okay, so this is what with respect to the serial in, parallel out. Okay, so next we will move to the parallel in, serial out. So next we will move to the parallel in, serial out. So here we need to give the data input in a parallel, so that means we need to use the A, B, C, D. So these pins will going to be used so to give the input to the each flip flops. So whatever the data will be given to these pins will going to be loaded into the each flip flops. Okay, so where the A flip flop corresponds to the MSB, and the D flip flops corresponds to the LSB. Okay, the connections of an 7495 to implement the parallel in, serial out. So here the 4 inputs will be given. So whatever the data we need to give, that will be given here. Okay, and we are taking the data in a serial out. So that means only the last flip flop output is needed. So that's why we are going to connect only the QD. So QA, QB, QC will be not connected as similar to the serial in, serial out. Okay, the clock pulse will be given for the even the serial clock and even for the parallel clock. Okay, so we are going to explain that one, when to use the serial clock and when to use the parallel clock. Okay, and the mode pin will be connected, and as usual VCC and the ground. Okay, so here first we need to load the data into the parallelly, so to the all the flip flops, and then serially we need to be shift. Okay, so for that one first we need to keep the mode pin to the 1 and apply the clock pulse to the parallel clock pulse. Okay, so what from the clock pulse to the we need to connect it to the parallel clock pulse, and we need to connect the whatever the input we need to be give. Okay, so here we have taken the inputs are 1 1 0 1, QA 1, QB 1, QC 0 and the QD 1. So that corresponds to the 1 1 0 1. When you give this input and apply the clock pulse, the flip flops will go on to store the corresponding inputs. So that is 1 1 0 1 will going to be stored. Okay, then change the mode pin to the 0, because now we need to do the serial operation. First we done the parallel operation, so that's why we kept the mode pin to the 1 and store the data to the flip flops. Now we need to change the mode pin to the 0 and we need to give the clock pulse to the serial clock. Okay, so as when the giving the clock into serially, the data will be shifted. See here at the time t naught, okay, all the data will be stored here. Okay, when it comes to the next clock pulse applying to the serial, where we are doing the serial operation, when you apply the clock pulse, this data will going to be shifted to the next flip flop. Okay, so this data will be shifted here, this data will be shifted, and this data will be shifted. Okay, and here whatever the data will be given, that will be enter. Okay, it can be give 1 or 0, so that's why we indicated with the don't care. Okay, next when you apply the next clock pulse, and this data will be shifted here, this data will be shifted here, and again apply the clock pulse, we will going to get the last data. So this is how we will going to get the serially output for the inputs where we are given 1 0 1 1. So that is available in a serial, okay, where the data will be given in parallel. Okay, so this is what the parallel in serial out. Okay, so keep in mind here, first mode pin we should be 1 when you need to store the data into the shift registers, okay, and then change the mode pin to the 0 and apply the clock bus. So when you are storing the data, we need to use the parallel clock bus, okay, and when you shifting the data, so when that is mode pin equals to 0, then we need to use the serial clock bus, okay. So this with respect to the parallel in serial out. So next we will move to the parallel in parallel out. So next we will move to the parallel in parallel out, okay. Here the data will be given parallelly and even the data will be taken in a parallel. So that means we need to operate the shift register in a parallel mode. So that's why keep M mode pin to the logic 1 and apply the clock bus to the parallel clock, okay. So and the data will be given to the all the flip flops. So the shift register should store the all the values, okay. So that is what 1 1 0 1. So this were the all the inputs will going to be used and all the outputs will going to be used because parallelly we are giving the input and we are taking the output parallelly, okay. So here we have taken the data 1 1 0 1. So this will going to be stored in the flip flops when I give the clock pulse, okay. But at the time only we will going to get the output at the each outputs. At the time only we will going to get the output parallelly, okay. So this is what only at the one time clock pulse you are giving. So we are going to give the input and we are going to take the output, okay. So this is what with respect to the parallel in parallel output. Okay, next we will move to the implementation of a ring and Johnson counter. So first let us understand what is a counter. So counter is also a cascade of flip flops, okay, configured to a output or a specific sequence, okay, on application of a clock. When you give the clock, okay, a specific sequence will going to be repeated in a shift register, okay. So that is what is called as an actually a counter, okay. Assuming that one we have the 3 states. As upon the clock pulse is given, okay, so the first S1 state will be moved to the S2 state and the S2 state will be moved to the S3 state and S3 state will be again moved to the S1. So that means assuming that one we have the this S1 state corresponds to the 4-bit shift register is 1001, okay, and that is the next one is 1100 and the next is what 0110. So these are the 4 states we have, assuming that, okay. When you apply the clock pulse on the first time, so this state will be moved to the here. So that means 1001 will be the states of the shift register and value, okay, that will be changed to the 1100. And again if you apply the clock pulse, okay, then this data 1100 will be changed to the 0110 and again if you apply the clock, again we will going to get the 1101 like that. So this is what is a counter, okay. So specific sequence you are going to get on application of a clock, okay. So here, so we are going to use the same 7495 only, so that is for the shift register. So we are going to configure that one so that we need to get an output a specific sequence, okay. So that is called as an actually a counter, okay. To implement a ring counter, how to change the circuit, how to configure the 7495, let us understand, okay. So next we move to the ring counter. So ring counter is an counter where the output of one flip flop is directly connected to the input of another flip flop, okay, and we will going to produce a specific pattern, okay, and it is also a circular shift register, okay, where the initially the only one of the flip flops will be set to the 1 state and the remaining will be in the 0 state, okay, and then the serially will going to be shifted. That is what a ring counter, okay. So here we can see, so initially the QA has been set, okay, and all the other will be the states of the flip flops are 0, okay. Next, as the giving on the clock, okay, this data will going to be shifted here. Next, this data will be shifted here, this will be shifted here, and again this data will going to be shifted here. So that means, so this will be in the first state, okay. Again if you give the clock pulse, so that will be moved to the second state. So this is the first state, that is 1000. When you give to the next clock pulse, then that will move to the 0100 state, okay. If you give to the next clock pulse, 0010 state, okay. Next 0001 state, again if you give the clocks, then this again will move to the first state, okay. As I already said, so when we are having the S1, S2, S3, S4. So this specifically the states will going to be repeated. That is what is an counter. Okay, so this is what here. So first you will be having a 1 0 0 0 state. Okay, when you give the clock pulse, this will be moved to the second state. Okay, and again if you apply the clock, so this will be moved to the third state. Okay, if you give the clock pulse again, so this will be moved to the first state, and again if you give the clock pulse, that should move to the first state. So this is what is an a counter. Okay, where ring counter will be having again initially one state of the any flip flop will be 1, and that will going to be repeated. Okay, here we have taken a QA equals to 1. Okay, so that will be shifted after at the time of the fourth clock pulse. At the time of the fifth clock pulse, we are going to get the first state. Okay, again if you give the clock pulse, that will move to the second state. Okay, so this is what will be continuous. So that is what is called as a ring counter. Okay, so to achieve this one, actually how to connect a 7495. Okay, if you see here actually, so 1 0 0 0 is there. Okay, and here QD is connected to the QA. Observe, so this 0 will be shifted to here, and this one will be shifted here, this 0 and this 0. Next, this 0 will be shifted here, this 0 1 0. Next 0 is shifted here, 0 0 1. Next this one is shifted here. So then only we will going to get the our first state. Okay, so if you connect a QD to the input for an A flip flop, okay, the first flip flop, okay, so then we can achieve this ring counter. Okay, so this is what the connections we need to do. So as usual, VCC ground will be connect, okay, and the mode pin. So here mode pin will going to operate in a both the mode, parallel mode and in the serial mode. So that's why we are going to use the both clock pulse, serial clock pulse, and even for the parallel clock pulse will going to be used. Okay, and here A, B, C, D inputs will be initially will going to be load, so that particular specific pattern we need to store where the any one of the flip flop state should be 1. Okay, so here we have taken a QA will be 1, so other states will be 0, so that means A should be 1 and the remaining output must be 0. So to achieve that one, we need to keep the mode pin to the 1 and apply the clock pulse. When you are keeping the mode pin, that means parallel operation, okay, and apply the clock pulse, we will going to store the corresponding values to the specific flip flops. So that means QA will going to having the value 1, QB 0, QC 0 and the QD 0. Okay, to achieve this pattern accounting, okay, where QD will be connected as an serial data input. Okay, because this should be appear here, then so when you give the clock pulse, this data will going to be shift, but this data should be given as an to the input. Okay, for that one only, so QD will be connected to the serial data. Okay, so when you apply the clock pulse, okay, serial clock pulse, okay, first we need to set to the mode pin to the 1, okay, give the 1 0 0 0 pattern to the flip flops. So that means all the 4 flip flops are going to have the 1 0 0 0 value. Now change the mode pin to the 0 because we need to do the parallel operation, okay, and they give the clock pulse to the serial clock pulse. Okay, when you give the serial clock pulse, okay, this data will going to appear here and this data will be shifted here, this will be shifted and this will be shifted to QD. Okay, so this is what will going to happen. So again, so this QD will be connected to the serial data. So this data will going to appear here when you give the next clock pulse, okay, and this data will going to be shifted to here, this data will be shifted here, this data will going to be shifted to here. Okay, on that time we are going to get the pattern 0 0 1 1. Okay, when you give the next clock pulse, so this data will going to be shifted here, so this will be shifted here, this will be shifted here, this will be shifted here, so that we are going to get the sequence 0 0 0 1. Again if you give the clock pulse, okay, this data will going to appear here and this will be shifted here, so that we are going to get the our first state, it is 1 0 0 0. If you give the one more clock pulse, this will be repeated. Okay, this is what is a counter. Okay, so this is what with respect to the ring counter. So keep in mind, first we need to be set the mode pin to the logic 1 and the load the parallel data. Okay, and then set the mode pin to the 0 and give the clock pulse to the serial clock pulse, so that we will go to achieve the ring counter. Okay, so next we will move to the Johnson counter. So next is the Johnson counter, where Johnson counter is also called as a twisted ring counter. Here, so whatever the data will be there in the QD, that will be complemented and will be given to the QA. Okay. So, in the earlier ring counter actually 1 0 0 0, this data will be directly given, okay, and then the sequence will going to be repeated, right. So, this will go to be 0. So, that is why we got a 0 1 0 0 in the ring counter, but here a twisted ring counter. So, that means what, a Johnson counter, okay. Here, so the last data of the flip flop will be a twisted, that means what we can say complemented, and will be given to the a serial input, that means the first flip flop. Okay. So, that type of connection or that type of counting sequence, that is will be called as a Johnson counter. Okay. You can see here actually 1 0 0 0 was the initial state, and this will be complemented. So, 1 will going to be coming here, and next 1 will be shifted here, 0 will be shifted, 0 will be shifted. So, that we are going to get the 1 1 0 0 sequence when you apply the clock pulse. Next, when you apply the one more clock pulse, and this 0 will be complemented, will come to the 1, and next this one will be shifted here, this one will be shifted here, and this one will be shifted to here. So, this is complemented. Okay. Next, again if you apply the clock pulse, so this will be complemented and will be shifted here. Okay. So, like that will be continuous. Okay. So, similarly 1 0 1 1 1, 1 becomes a 0 0 1 1, next 1 becomes a 0 0 0 1, next 1 becomes a 0 0 0 0, next 0 will become a 1, okay, next 0 0 0. So, this was our first step. Again if you apply the clock pulse, and the second sequence will going to be repeated. Okay. So, this is what is called as an Johnson counter. So, now we need to implement this one by using the IC7495. Okay. Okay, for that one we need to connect the 7495 as usual as the ring counter, where the QD will be complemented and it will be given to the serial data. Okay, because so this should be complement, okay, and the remaining will be the as it is. Okay, so that is why. So, will be complemented. Okay. So, here also first mode pin should be Z1, okay, to do the parallel operation and give the whatever the sequence we needed. So, that is what 1 0 0 sequence is needed, that will be given, okay, and apply the clock pulse. So, that clock pulse should be a parallel clock pulse, so that all the data will going to be stored. Next, change the clock pulse to the serial and the mode pin to the 0. Then apply the serial clock pulse, then we will going to get the 1 1 0 0 sequence. Okay, that means we are going to get the 1 1 0 0. Next, again if you apply the clock pulse, and then this will going to give the next sequence 1 1 1 1 1 0. Okay, similarly like that. If you give the clock pulse, next will going to be continuous. Okay, so this is what with respect to the Johnson counter. Okay, so this completes the experiment number 8. Okay.